Welcome to Textile Update, the podcast where we can share our passion for textiles, fibers, and yarns. This is Gwendolyn Hustvedt. This is the fourth in a series of 5 podcast episodes where I look at finishes, and the first in a set of 2 where I'm focusing specifically on functional finishes. So why would we change the functional performance of a textile? Why would we apply a finish after we're done manufacturing the textile in order to change it and help it do something else? Well, in many cases, this is because certain fibers don't have the performance that other fibers have, but we'd still like to use them because of other properties. So, for example, we discovered that synthetic fibers don't wrinkle as much, so we don't have to iron as much. But we really like the comfort and absorbency of cotton. So we need to come up with a finish that gives us the performance we've come to expect from a synthetic, but with the comfort we expect from cotton. Or in the case of wool, we'd really like to use it. It's warm, it's soft, it's enjoyable, but it has a problem with laundering. So if we can make it felt resistant, then we can use it in more settings. And of course, in some cases with thermoplastics, we need to heat set it in order to get it to have the texturized appearance that will make it imitate a natural fiber. So very often the finish is about getting the best of all worlds. I'm going to group the finishes into big categories. So stabilization, comfort, water resistance, stain resistance, UV resistance, organism resistance, flame resistance. That gives us an idea of what the purpose of the finish is. As I've mentioned in the Routine Finishes podcast, we're going to use a pad application to squeeze the foam or the paste or the liquid or whatever it is into the fabric. And this is a great method because it allows us to very precisely calibrate exactly how much finish we're applying. And when I explain to you that some of these finishes have downsides, right? We want to make sure we only have enough finish to get what the properties we desire without having so much finish that we start to get properties that are undesirable. So one way we could do this is we could have the fabric travel over a roller down into a vat that contains the finish, travel up out of the vat, and then be pressed against a sponge roller that's and a solid metal roller. And the tighter the solid metal roller squeezes the fabric against the sponge roller, the more the finish is going to be pressed off of the fabric and onto the sponge. So we can adjust how much finish is on the fabric just by adjusting the tension between the sponge roller and the flat metal roller. And this is an important responsibility for people who work in finishing facilities. I could spend a whole lecture talking about the innovation of nano finishes, right? But let me just say that the idea with a nano finish is that we're applying the finish down at the molecular level. It's a very durable finish, and so this means that instead of just dipping the fabric into a big vat full of the liquid with the finish, we actually create a system that delivers molecules of the finish to the surface of the fabric. So we have exactly the amount we need to bond with the fabric and no more. So you might see some technologies like NanoCare or NanoTouch, and the idea is that we only have just the amount of the finish that we need because it's been applied down to the molecular level. So I just want to let you know that the pad finish method, it's the older method. It's not the only way to do it. I mentioned durable press as being a very popular finish with cotton, and this is because cotton has a problem with wrinkling, with resiliency. So if we can add resins that cross-link between the polymers inside of the fiber, then we can, in fact, keep the fibers from changing shape at all, which will end up not only helping with wrinkling, but also helping with shrinking. So we apply the finish and then we heat set it, or quote, cure it, right? So we'll see big curing ovens where the finish is heat set. I saw this when I was in the Dominican. There were some dockers that were sprayed with the finish and then traveled through an oven. And this was after they'd been ironed. So now they're going to stay perfectly crease free after that. Disadvantages to the durable press finish are several, right? And it's important to know this finish is actually one of the big reasons why we have textile testing facilities, because if we have a finish that degrades the strength of a textile, we want to make sure that we can prove, firstly, that the finish is performing correctly by doing a resiliency test. So we'll actually scientifically try to wrinkle the fabric. And then we'll also do a tear test or a strength test using an Instron or a tear test machine to see if the fabric tears so easily that it's not fit for end use. So things like uniforms used in fast food restaurants will end up wearing out a bit more quickly, even though they don't wrinkle as much. And so it's a balance we have to find. These finishes are also oleophilic, so that's why you smell like fries when you come home from your shift at the fast food restaurant, because the grease from the fryer is in fact attracted to the finish on the surface of your uniform. And they don't elongate as much, and they have less absorbency. So overall, again, not insurmountable. It's just important that we have the exact correct amount of the finish applied to the textile. I've talked about anti-felting finishes before, but just to reiterate, these finishes that create washable wool typically do so by destroying the scales, so using chlorine bleach, a process called halogenation to remove the scales. This does not improve the hand, and it does not improve the strength. All it does is make it so you can launder it, right? So it only improves dimensional stability, but it does not make it shinier, right? Just like bleaching your hair doesn't make your hair shinier or stronger or softer, right? It just makes it a lighter color. In the same way, the anti-felting finishes don't improve the wool, so it's really important that we only use enough to reduce the felt tendency to the point that the consumer is happy and not any extra. Now, when it comes to dimensional stability, shrinkage is a huge problem for consumers. They don't want to buy a product that then makes them feel, overweight, or that makes their kids look like they're wearing clothes that are too small for them. Fabric typically will shrink the most right after weaving. So we call this relaxation shrinkage, which happens because the tension of weaving is removed. The warp yarns are under tremendous tension, and the first time that it's laundered, they relax back to their original length, which is shorter. But then there's also such a thing as progressive shrinkage. Every time a wet fiber swells, it grows in diameter and shortens in length, and if this happens over and over, then over time the yarns just end up shorter, the fabric ends up shorter. So we need to find a way to solve these problems. For relaxation shrinkage, we have a couple of different methods that we can use. The method that we use on wool is called London shrunk. It's just a gentle, delicate process that helps to remove the relaxation shrinkage. It's not anti-felting, it's not fulling, and I don't even know if it was invented in London, but that's what you could see on a label, or you could ask a supplier, has this been London shrunk? It's just a fun thing to say, London shrunk. For wovens, we can add a portion to the finishing process, which is called compressive shrinkage. Basically, we just have two rollers that are moving at very different speeds. The first roller is moving really fast, the second roller is moving slow, and the fabric basically flies over the first roller and then crashes into the second roller. And just like the front of a car crumples up when it crashes, the yarns are kind of crashed into each other. And believe it or not, this works. We can see that it increases the fabric count, right? The number of warp and filling yarns in 1 inch. And so it works. Now for knits, we'll do a slightly different process called compactor shrinkage. So we'll basically feed it through rollers into a box, and it's sort of all crowded in there, and that causes the loops to try and assume their ideal size and shape. And then, of course, to deal with relaxation shrinkage in thermoplastics, we just use heat setting. I've mentioned heat setting before, but let me unpack it for you a little bit. Synthetic polymers have a melting point, right? You heat them up to a certain point, they're going to melt. Try with an iron on, no, don't, but you get the idea. Like if you took something plastic, you could melt it. But all materials have a temperature that we call the glass transition temperature. That is the moment right before they melt. I've actually seen this. When I was a college student, I took organic chemistry. Oh, Dr. Miller, it was such a great class. And in the little lab area under the stairs, yes, we had to go into a little closet under the stairs. There was a narrow bench there, and sitting on it were special microscopes that were attached to heating blocks. And we would put the chemical compound we were seeking to identify, we'd put one little crystal of it, let's say salt, into a tiny, tiny plastic glass tube. And so we would tap the glass tube against a pile of the salt, and then we could look at it under the microscope and see that there was one little crystal of salt inside this glass tube. Now the microscope was kind of cool. It was like binoculars, and with one eye you were looking at the glass tube with the one crystal of the material in it, and with the other eye you were looking at a thermometer. And what you were doing is you were waiting until the moment right before the crystal melted. And the moment before, the crystal gave a little shiver as the amount of energy being provided by the heat caused the bonds in the crystal to realign. And then just after that, it melted. Okay, so you were looking for the temperature when you first saw it give a little shiver, like it would actually settle a little further into the tube. So we know that temperature for thermoplastics as well. And so we'll heat them up to just where they're feeling relaxed, but not where they're like actually melted. This improves the resiliency by allowing all the bonds to be at their shortest length so that they're ready to stretch back out again, and relaxes any tension that happened during weaving. So nylon, polyester, acetate, these are all fibers that we can heat set. Now, besides relaxation shrinkage, which we want to deal with, we may say, oh, but we want to deal with progressive shrinkage. We don't want it to shrink anymore. There, the same cross-linking agents that we used for durable press can also be effective. So I already mentioned those. And we can also just pack the pores in the fabric with a resin. And this is great for indoor-outdoor material where we don't mind that it's now no longer absorbent. We just don't want it to shrink because it's in the rain. So the yarns can't change their length or their diameter because the resin has filled the interstices, the spaces between the yarns and the fabric, and have filled it all up. Right, and so that is certainly not something we would do with apparel fabric, but can be great for a lot of industrial purposes. So that's dimensional stability. In the next episode, I'm going to talk you through comfort, which is a very important property. And then we're also going to look at some of the more exciting things like flame resistance or UV resistance that are important for safety performance in many cases, as well as stain resistance, which isn't so much a safety issue as it is something that's very annoying when it comes to stains in your carpet or upholstery.